Okay, so last video we understood what the data is and we kind of looked at it from a bird's eye view. Today we're going to load the data for Google File Source Load Predict AI Model Runtime. And we're going to understand all the fields of the data. And we're going to do it in this nice Kaggle notebook right here. And because of course you have to load the data with some kind of purpose, we're going to load it such that we can put it into a PyTorch geometric model, which is like a pretty standard machine learning library for graph neural networks for PyTorch. PYG, it seems pretty good, it seems pretty standard. We're going to load it so that it goes into PYG. Okay, so I'm assuming that you already understand what the competition's about. I'm assuming that basically you're at a level of knowledge such that you know, the same level of knowledge that if you just watched the last video. And all we're going to do now is we're going to start loading the data. So just first some basic imports. And now let's actually have a look at the data. I happen to know already from my previous experience that the data is sitting in here. Or rather, the tile-related data is sitting in this directory. So yeah, we're just going to use that directory and then we're gonna have a look at what is sitting in that directory exactly. Okay, so great. TileXLA contains valid, train, and test. These are sort of like three splits, and we're just going to be working on train today. We don't care about the others. Okay, and inside we see all these files, and each file kind of looks like it's part of a neural network, as you went over before. Basically what this means is that each of these corresponds to like a subgraph taken out of a neural network. So, for example, RetinaNet 4x4, this one is like some small subgraph that has been taken out of a RetinaNet model that's been running on Google's TPU hardware. Okay, so let's just like select one of those and see what exactly is inside it. Okay, so you load this data and then you've got this .npz object. Sort of a pro tip, if you turn this into a dict, it'll actually load all of that stuff into memory, whereas at the moment, this data is actually like not yet loaded. It's being like lazy loaded. So if we do this, it'll actually put the data in a dict for us. And it'll actually put it into RAM. Okay, so this is kind of what we're looking at. We're looking at a dict. It's got these keys and it's got these values, but let's actually just sort of, let's get a closer look. Let's get some shapes and stuff going. And so let's just talk about these a little bit and make sure that we understand them before going on and actually loading anything. So node feet, this refers to the features for every node in this graph. And in this case, there are 31 nodes, and each node has 140 different features. Sort of just to give you a bit of a visual aid, I've made a little diagram here. This is another graph. This graph only has 4 nodes in it. And you can imagine that just like the nodes in the graph here, the subgraph of the RetinaNet, you know, these nodes might also have features. You know, like for instance, we might know that this node, it's a root node. So we might be like, oh yeah, this node has the isRoot feature. That feature is on that node. And maybe it also has the hasKernel feature. Maybe it, I don't know, has something like, I don't know, window, maybe it takes no inputs so that we know, you know, the has 2 inputs feature is like false, right? Like these are both true. And we might set up one of these for every node. Like there are some features that are true of every node in this diagram, you know, including this one, including all of these ones as well. They have different features. So that's all this is. This graph has 4 nodes and 3 features per node. And this graph here apparently has 31 nodes and 140 features per node. The actual names of the features you can find in this data section of the competition. These are all the features that are allowed. isRoot, you know, the shape of the dimensions, window sizes, layout minor to major. There are a lot of different features that can be extracted about every node in these graphs. Okay, so that's node features. Hopefully we can kind of understand what that means. Okay, now we have node opcode. What that refers to is each node has a different operation that it's performing. So this might be like an add operation. Maybe this is a multiply. And this is another add. And this here is like, I don't know, it's like a min, for instance. Okay? And you can imagine that, like, rather than actually spelling out min, add, multiply, we might just keep an array sitting somewhere in memory that just, like, you know, has the node indices. And so knowing this, we might just have an array which, firstly, we have an array of different operations that exist. So it's like add, mult, min, max, sub. Maybe in here is like, I don't know, arg, max. Maybe the, you know, who knows how many operations there are. And to sort of say what the operations are of all the nodes, you might create another array which just says for each node what is the index of its operation. So node 0, that's add, so 0. Node 1 is min, so that's 0, 1, 2, 3. Node 2, that's mult, so that's 2. And then add again, so that's 0. Right? And like this array now specifies for this graph what all the operations are. And that's all node opcode is. And let's actually have a look at node opcode. Node opcode. Okay, so it's kind of exactly what we thought it would be, right? It's like an array, and it's just got all these different integers, and each integer stands for an opcode. If you actually want to see where the opcodes are, you have like two options. The first option, kind of annoying, is you have to go to the GitHub repository that's related to this project. So in the GitHub repository, all the opcodes are actually listed here in this really long array. Another little fun alternative is that earlier I made a notebook, which I used ChatGPT to just like state what all the opcodes are. So if you look here, there's actually like in a Python dictionary, I've chucked all the opcodes, and I've also chucked a whole bunch of other different things. So that might be kind of useful. Yeah, if you actually want to know what the operations are, rather than just looking at the numbers that it gives you here. Okay, so that's node opcodes. Then we have edge index. And the idea here is that all this does is this specifies which nodes are connected to which nodes. And yeah, it always shows the output first and then the input. So let's actually have a look at that. Okay, so we can see the shape is like 33 by 2, which means that there are 33 different edges. And yeah, 33 different edges. And the way it specifies an edge, it says, here's the output, and then here's the input. So node 2 is the output, and node 0 is the input to this edge. And if you look down here, node 26 is the output to a different edge, and node 18 is the input. So again, if we want to visualize this, okay, how many edges there are? There are like 3 edges. And we can create this sort of edge index array. So let's give indices to our edges, 0, 1, 2. Okay, so this is the 0th edge, and what's the output? Output is node 2, input is node 0, great. Next one, output is node 2 again, input is node 1. And finally, output is node 3, input is node 2. Okay, and so that's edge index now for our little like more basic graph. And this is node opcodes. Okay, right. So between these 3 different pieces of data, the node feet, the node opcode, and the edge index, if you look at all of them, you will get a full specification of the graph in question. Those 3 together, they tell you everything you need to know about this graph. You can construct the graph, and you can use any kind of visualizing software you want to visualize the graph. Okay, these next 3 variables, they relate to trials Google have done with that graph. So in this case, it looks like they've done 1,537 different trials. And each time they've done a trial, they've chosen a new configuration for the tiling. And if you want to know what tiling is, it's covered in my previous video, and it's also covered throughout the competition. Essentially, it's a way to specify how to break up tensors. So rather than having a big tensor, you can have like many small tensors and do operations on them in parallel. And it's just like, how big or small do we make those small tensors? That's what tiling's about. Okay, so they've tried 1,537 different tiling configurations. For each configuration, they've specified the configuration in config feet, and then they've specified the runtime, which is how long the configuration took to run when Google ran it. And then they've also given us a normalizer for the runtime. So basically, we'll go normalizers, we'll do that at the end, but this is all the data that relate to the trials that have been done for this graph. Okay, graph information, trial information. So let's have a look at what config feet actually looks like. And so this is the first trial that was done, and the config looks like this. Great. And I happen to kind of know what this is, and I guess we can look into exactly what it means. But basically, it means that the max length of the 0th dimension of any tensor in this graph will be 16. So, if we have like a nice big tensor, we imagine we have like an 8x10 matrix sitting in memory. A tiling of that says 16, 16, that says that the maximum length that we're allowed to have when we're processing this on the either dimension, the first or the second, is 16. And if it was like 4, 4, if it said 4, 4 instead, then it would mean the maximum dimension is 4. And then when actually processing this, we'd have to break the tensor up into these tiles of 4x4 whenever we actually wanted to perform any processing. So that's, so like the actual tiling strategy was 16 by 16. Another tiling strategy could be like 4x4, etc., etc. And the idea is that some tiling strategies will be better than others. If you actually want to look at exactly what those values mean, again, data tab, and you scroll way down, and it tells you what those 24 values actually refer to. So like, here, right? Kernel bounds 0 and kernel bounds 1. Those are the first two elements of the tiling configuration. And we can see here, 16 and 16. So like in both those cases, for both those bounds, it's 16. That's the biggest you're allowed to have a tensor be on either of those bounds. And then we've got all zeros after that, and it tells us that a 0 just means that like there's no specification, and we don't care about the tiling configuration for anything, any dimension that has a 0. So in this case, we're going to start breaking up tensors on the 0 in the first dimension, and we've got a 1 here. We've got a 1, crazily enough, for the third dimension, which means that you have to tile every single goddamn like number individually, which is a bit crazy and wild. That seems like a very strange tiling configuration to have. But this data set, I believe they tried essentially every single possible tiling configuration, so you're going to get some weird ones. And then on the third dimension, they've set the tiling to 2, and then on the 5th dimension, they don't care. And you can do whatever you want on the 5th dimension, and the same with the 6th dimension. There's like no restrictions there. And then it also gives you the sum and the product of those dimensions. And the first 6 or 7, how many is it? Yeah, the first 7 numbers pertain to the output, and then the next... the first 7 actually pertain to the kernel. I wasn't aware of that. And then the output and then the input. So we've actually been looking at the kernel tiling strategy. As we can see, the input tiling strategy also kind of weird. The first 2 dimensions have a maximum bound of 1, which is kind of odd. And then 64 and then 2. Okay, so we can kind of understand what this config means if we have a look at, say, a different config number 100. You can see it's completely different. They've got different bounds specified. They've got different sum and mult. 160. Okay, completely different again. So these are all many different configs that have been attempted. In fact, they've attempted 1,300 1,537 is the number that they've attempted. Okay, great. So now hopefully we understand what config feat is. Config runtime. Well, let's just have a look at config runtime. What does it look like? What do we have here? What kind of strange things we can encounter? Okay, it's all these like really big numbers. And in fact, let's just have a look at what the mean is. Because I imagine it's pretty high. Okay, we're looking at what? What's this? Like 900,000 is kind of roughly what the runtime is. And you might think, okay, well maybe this is in like nanoseconds or something. The reason it's so high is that the way you're supposed to interpret this is you're supposed to divide it by the normalizers. I'm actually unsure as to why they've stored it like this with the runtime and the normalizers rather than just having, having performed this piece of mathematics first. But this is the way you're supposed to interpret it. Like the actual runtime is the runtime divided by the normalizer. And we do that, and then if we look at the runtime, the numbers seem like, a lot more reasonable. Yeah, so like the mean is now a more reasonable number. It's like 3.9. And maybe it did take 3.9 seconds or 3.9 milliseconds to run this node. Okay, and then of course, let's just like plot the mean here, because that seems reasonable. Like what kind of, runtime, nice. What kind of, so it's like, okay, runtime is mostly sitting down here in this section. Let's ask for some more bins. Yeah, okay, so it's kind of like a little nubbin here at maybe like 9 or so, but a lot of them are almost 0. So this is the kind of runtimes we're looking at. Hopefully this all makes sense. Now what we're going to do is we're just going to actually load it into a format that we can use for training a neural network. So given that that's the objective, the first thing that we have to do is actually, make the neural network. And in another video, we're going to focus a bit more on the neural network and talk about how it works exactly. But for now, we're just going to try to import this library, Torch Geometric. It's going to fail, and we're going to have to install that library using pip. And then we're going to use that library to define this neural network. Essentially, it's like a fancy kind of neural network that takes in the config. It takes in, so that'd be the config feat here. It takes in the node features, it takes in the opcodes, and it takes in the edge index, and then it performs, it runs all of those through its convolutions, and then some linear layers, and then it returns like a prediction for what the runtime would be, given that config, those features, that opcode, and the edge index. So we're just going to load the data into such a format that that model can take it in. And that's where we're going to stop. That's where we're going to stop, because we don't want to make this video 1,000,000 billion hours long. That's something we want to avoid. Okay, sorry. So I'm just finishing off the imports here. Okay, great. So now we've loaded this, and we actually have this model here. And great, this is what it looks like. It's pretty small. I think it's only got like 17,000 parameters. Tiny model. And again, like we're kind of looking for this kind of input, right? Config, then feat, then op, and then edge index, and it'll all have to be torch tensors for us to actually be able to load it in. That's fine. Okay, so we have all our file names. We already have them already here. So let's just start for file in file names. And we're going to make it a bit easier for ourselves. We're only going to load the first file name, because I happen to know the second file name, sorry. Because I happen to know the second file name hasn't got many trials in it. If we look at the second file, which we know what it is, it's this one here. It's the RetinaNet 2x2. It's only got like, okay, maybe I'm completely wrong. I think I was actually using the valid before. Yeah, okay, so the second file in the valid only has like 286 trials. It doesn't have like a large number of trials, so that's a good one to start with. Okay, so like for files in file name 1 to 2, so that'll just be loading that one file. You know what, let's just confirm that. Print file. Great. Okay. So what we want to do for that file is we want to load all the data that's needed by the model, so the config, the feat, the op, and the edge index, and then we also want to load the runtime, right, as well, so that we can use that to like do the training. Now I happen to have written all this code earlier, and I feel like there's not much benefit me just typing out in front of you. So I'm just gonna paste that in. And in order for it to work, we just have to define this graph data variable. So data equals np.load file, and then we just have to turn that into a dict. And then we need trial index. We're doing like because what we're doing is we're only loading one trial at a time, right? We know that there are 280 different trials. We only want to feed one into the model at a time because we want to go like really slowly and carefully. So for so we load the graph data first, and then we ask for the, what is it? Config runtime, because there's one runtime per trial. So then we just say range. We say like, you know, one for each index, you know, for every index such that there's one index in config runtime, load that index's config feats, load that index's node feats, load the opcodes, and then grab the runtime, divide it by the normalizers, again for that particular trial, and then convert to a float 32. And of course, in all these cases, we're like converting these from NumPy arrays, which they are at the moment, into torch tensors. And also for the edge index, we have to permute it because the shape of the edge index at the moment is like number of trials. No, hang on. Yeah, number of edges and then number of nodes per edge, which is always 2. And the model expects the opposite. It expects the edge index to have the 2 and then the number of edges. So we just have to like switch that around. Okay, cool. Yeah, and then we'll break, and then I guess we'll just like print, I don't know, print config feat. And then we'll break, just to see if this has actually worked. Great, it's worked. It's a tensor, and let's just print its shape of shape 24. Okay, great. So this is like, this seems to be working. Seems to be working nicely. For like a little bit of optimization, we happen to know that the node feat and the node opcode doesn't change. These remain the same for every file. And we know this because like every trial for each, you know, each file corresponds to the same graph. So these two variables do not change depending on the graph. The things that do change is the configs, the runtimes, and actually edge indexes don't change either. So we don't have to load them every time, which is just like a nice little extra thing for us. Okay, that all looks pretty good. And let's just print the shapes here. Actually, we already know what the shapes are. You know, we've seen what those shapes are going to be. Okay, so that's really good. Next, let's just parse this into the model. So output equals model, and then what's the order of the model? Config feat. Great. Yep. So then we want the features themselves, so node feat. And then we want the opcodes. And then edge. And we'll print the output. And again, this is just one sample, so the output should just be like a scalar. And we'll also print the runtime. And if we're lucky, this will work. It probably won't work though. Okay, what's the issue? Dimension out of range. Right. And the issue here is that this code was originally written to take in many different configurations at the same time. And we're passing the configurations in one by one. So all we have to do is we have to unsqueeze it in the 0th dimension. So now rather than being of shape 24, it's of shape 124. And instead of 1, we could have like 7 or 8 or like 128 different ones being passed in as a batch at once. But at the moment, again, we just want to be really slow, so we want to break, do it one at a time. Okay, great. So the prediction was 360, and what actually ended up coming out, what the target actually was 1. So that's really good. You know what? Let's just do it for all 86 of these guys. Make sure there's no like issues. Okay, great. So we're predicting these really high numbers. Of course, we're not training the model at the moment. We're just passing the values in. But as we can see, like the runtimes are like 4, 17, 2, and the things being predicted are like 387, 385. So at the moment, the one thing that we can definitely know for certain is that our model is pretty bad. This is like a pretty bad garbage model, and that's what you'd expect, because we haven't trained the model, we haven't done anything with the model. This is a blank, empty model that I stole, whole cloth from someone else. So that's what we're looking at. That's what we're currently looking at. And of course, we could, at the moment, we're just doing for one file. We could load all the files if we wanted to. But this is how you load the data in order to put it into a PyTorch geometric model. And maybe this would be like a nice, good, fun starting point for someone who's just entered the competition. Next time, we'll actually train a model. And we're going to be following, this is actually really cool, something that Andrei Karpathy wrote. This recipe for training neural networks. So if you want to get a head start, this is something really cool and very readable. And if you're the kind of person who finds themselves training neural networks a lot, I would recommend reading it. We're going to be following this in order to actually train a neural network, and then maybe we can get a reasonable score in the validation set.